All right, good evening and welcome to our online class. In today's video, we're talking about magnetic field. All right, magnetic field. Let's consider two magnets. If you bring two magnets like this, okay, when we are very small, we used to play with two magnets. I did it, two magnets of maybe a south and a north pole, and you brought another one that is here, okay, that has a north and a south pole. Now, if you try to bring this north pole, if you leave this one here or leave this one here, you try to bring this north pole close to this one will be running away. It will be repelling it. It will be running away. We used to play with that thing. You understand? You'll be going around, it will be running, you'll be pursuing it. You understand? And it will get to a point where if you do not place it very well, they will magnet each other. There's a force that will now attract them. That is when you mistakenly place the north, maybe this one is now north here and south, and then I have this one here, and then I have the north and the south pole here. So anything that makes these two to come to try to get in contact with each other, they do what? They attract themselves. You understand? So the problem is, what makes this thing attract each other or repel each other? That thing is called the magnetic field. There is a force that makes these two people attract or repel. It is called the magnetic field. Now let me give you an example. If you enter your house now and maybe let me use myself as an example. I like rice very well, okay, stew. Well, if I enter my house and I'm perceiving that my wife's stew, I'll know that this woman is around and she's cooking. That fragrance has told me that something is happening somewhere. You understand? The first thing I rush is direct to the kitchen. I rush direct to the kitchen. The fragrance has attracted me to that pot. Are you getting it? So that fragrance that is attracting you is called what? Is the magnetic field, if it is a magnet. Right? But maybe you enter your house and maybe a rat died, and then the smell is very bad. You will feel it. It will pursue you away. You understand? So that smell that is making you run away is what we call the magnetic field. Is what we call the magnetic field. All right. So now, having this thing, having known what is a magnetic field, so the next thing you need to know is the magnetic field line. Okay, we need to know the magnetic field line, the line of action of that fragrance, okay, of that force, of that field. All right. So the magnetic field line runs from the north. It moves from the north to the south. It moves from the north to the south. It moves from the north to the south. Okay, that is the direction. It's an imaginary line. We don't see that line, we imagine it. It's an imaginary line that runs from the north to the south of a magnetic field, of a magnet. All right. So this is it, from this to this, from this to this, and then from this to this. So moving this way. Okay. So this is and then we have this like this, then this like this. If it is coming from the south, it is moving inward. Okay. But if it is from the north, it is moving outward. Very, very important to note. If it is from the north, it is moving outward, but from the south, it is moving inward. That is outside the magnet. But inside the magnet, it moves from the south to the north. Inside the magnet, from the south to the north, inside the magnet. So you need to know that, so that it will form a complete circle. Having just one direction. They have just one direction. Okay, because if it continue moving from the north to the south inside, they will clash. Okay, and then you should know that what some properties of a magnetic field you should know is that, number one, the line moves away from the north pole and enters into the south pole. That is number one, you need to know. Okay, but that is for outside. But for inside, like I said, it moves from the south to the north. Okay, then the next thing you need to know is that the closer the magnetic field line, the stronger the strength. Okay, the strength of the magnet from here to here is stronger than from here to here. So the closer to the magnet, the stronger the magnetic field, or the stronger the strength of attraction or repulsion. So the more closer you are, if you bring this thing more closer, that is when it will repel it immediately. But if it is far apart, they may be here, they can stay here without moving. So the closer you move, the stronger the force of attraction or repulsion. That is one thing you need to know. Okay, then the next thing you need to know is that magnetic field line does not intersect. That's what I said before, they don't intersect, because if this one is moving from the north to the south and this one is equally moving from the north to the south inside here, there will be intersection. Okay, they don't intersect, they move on the same line, they move the same way, they don't intersect. Even if you bring another magnetic field like this one now close here, and this one is going this way, this one is going this way, and then like that, like that, like that, like I told you before, this and this does not intersect. If you get to the point where they will meet, they will follow the same direction, they don't intersect, like this one coming this way, the other one coming this way. No, they will change direction, they will move in the same direction, they don't intersect. Okay, that is one thing you need to know. Now another thing you need to know is what we call Oersted experiment. I don't know how to pronounce his name, but let me write it, then you can pronounce it. The Oersted experiment. This is O-E-R-S-T-E-D, Oersted experiment. Now there is something this man, okay, another thing you need to know, I forgot to tell you, is that to determine the strength or the magnetic field line or the direction of the magnetic field line, we use what we call a compass. We use a compass to notice that. Okay, when you have the magnetic field magnet like this, if you drop a compass here, maybe this is the north and this is the south, if you drop a compass here, a compass is a material that has a magnet inside of it, and that magnet has the red as the red sign as the north pole, and then the black sign as the south pole. Okay, if this is the north pole and this is the south pole, okay, once you bring it to this place, you will see that this thing automatically turns. It will turn immediately, so that this south will be here and this north will be here. It will turn so that this north will be attracting this thing, and the direction of a magnetic field is the direction of the north. We use the north to know the direction. So if you bring this thing close to this place, this one, if north was here before, it will turn to move like this, to show you that the direction of this man is moving outside. You see, this is the direction. It will turn to this side. So the direction of this magnetic field line from the north is outside. But if you bring it to this side, something happened. If you bring it to this side, look at what happened. The north will now be here and the south will be here, because the south had to attract the north. So you see that, and I told that the north is what we use in determining the direction of what? Of the magnetic field line, or the magnetic field, or the strength. So you see that for the north, the direction is inside. So that's what I said before, that it moved from the north and then move away from the north and then inside from the south. That is outside the magnet, but inside the magnet is the opposite, like I told you before. Please note that. So now let us now continue with this man's experiment. Now something happened. This man was just doing an experiment, or electrical experiment. There's a wire. He brought a wire here, but while doing it on top of his table, it was a mistake. It was a mistake. That was not even what he discovered here was not even the experiment he wanted to do. You understand? So this thing happened by accident. That's why we call it accidental experiment. So there is a compass on top of this table. This compass has both the north and the south pole. So something happened. This man brought he wants to do an experiment on, I think, electricity. He brought a wire. Then immediately this man passed a current to this wire. Something happened. This thing turned immediately. It deflected. And I say, wow. So when a current passes through a wire, so it produces a magnetic field, because the only thing that can make this thing turn is when there is a magnetic field in it. Like I told you before, if you bring a compass close to a magnet, the magnetic field will make the compass to turn. Magnetic field will make it to turn. All right. So therefore, when a current passes through a wire and it makes this thing turn, that means that the wire has a magnetic field there, and that is what brought about electromagnetism. So there is a relationship between electricity and magnet. So there is a magnetic force in a wire, or a magnetic field in a wire, whenever a current passes passes through it. So that is what we call that Oersted experiment, and this was discovered in 1820, please. In 1820, they said here, in 1820, a scientist made an accidental discovery that opened a new branch of physics that connects electricity and magnetism. He discovered that when a current is passed through a wire, it deflects a magnet. Like I told you before, it deflects a magnet. So, and this principle is used in all this equipment that you are using today, like your fan. Yes, this experiment that this man discovered is what is used in doing your fan, because if you plug your fan, immediately current passes through that wire, it will make it to start turning. All right, so that is what brought about that experiment. So now let's talk about the discoveries of his experiment. First thing, that he discovered that, now he now started, immediately that thing happened, he now said, okay, he now became interested in this thing and started looking at it to know what is really happening. Look at what he discovered. He discovered that if you increase the current, he increased the current here to know what happened. The increase in current brought about the increase, or it increases the strength of this this compound. It increases the strength. It makes it to even turn more faster. So the increase in electricity brings about increase in the strength of a magnetic field. All right, or increase in magnetic field strength. So please note that the first thing he discovered, what the experiment discovered, was increase in electricity or electric current brings about increase in magnetic field strength. All right. Number two is that the magnetic field strength is stronger when it is closer to the wire. Yes, he discovered, and I said, let me bring this electric wire closer like this. What happened? He made the current to remain the same, okay, and then decided to bring it closer. He discovered that the closer he brought it, the stronger the electromagnetic field strength. All right, and that is exactly what happened when you bring two magnets together. If you bring two magnets together, you are going to form a magnetic field strength. This guy want to bring down my camera. Sorry about that. So the closer they add to each other, the stronger the field strength. That is exactly what happened, to show that there is a magnetic field strength here. There's a magnetic field here. So that is why when you bring it closer, it becomes more stronger. Okay, that is number two. Number three is that the field line are in concentric circle with the center of with the center at the wire. Now he discovered that this magnetic field strength goes in a circular path around this wire. It goes in a circular path around this wire, while this wire remains at the center of that circular path. The wire is at the center. That is what he discovered. Now the next thing he discovered is that the direction of the field line is determined by drawing a tangent to the circle. Okay, that's another thing that he discovered. He discovered that the direction is by drawing a tangent to the circle. Let me say that there is a wire here. I don't really know how to draw, but just help me. There is a wire here. Look at the wire. Okay, this wire has a current inside of it, a current I. There's a current inside of it. Okay, there's a current I inside of it. Now this is going to go like this. Let's say that this is the circle now. Okay, now how do you determine the direction of this electric field? By drawing a tangent to that circle. So if there is a magnet that is here, you want to determine the direction of an electric field, a magnetic field here. Okay, what do? You draw a tangent on that place. You draw a tangent here, you see that the field is going upward. So if you want to determine the one under here, okay, at the bottom, you draw a tangent here. You see that this one is going east. If you want to determine for this side, this side now, okay, you are going to draw a tangent. To draw a tangent, you are going to see that it is going to be northward. Then if you are going to see here, you are going to draw a tangent, and you are going to see that this one is going to go west. This one is west. This one is north. This one is east. Where is south? Sorry, this is south. This is south. Now, somebody will say, why didn't I draw this thing the other way around? Why am I drawing it like this? It is because we use what we call the right hand thumb rule to know the direction of an electric field. The right hand thumb rule. Like if this is a wire, watch me. If this is a wire, okay, that has an electric current that is passing through from down to up like this, okay, we use the right hand thumb rule. We use our right hand to grab this thing like this so that our thumb will be on the direction of the wire. Are you with me? Just try and do it. So if this is an electric wire that has a current moving upward like this, I'm going to place my thumb to be moving upward. Then my hand is now showing the direction of what? The electric field. Okay, this is the direction of the electric field. So if I use my hand to place on this side, you see that I'm going like this. I'm going like this. So it's going this way. It is going like this. It's going this way. You see that according to my thumb. So if it is here and you are going like this, you see that it is up. If it is here, you are going like this. If it is here, you are still going the same way. Like follow the direction the thing is moving using your thumb. So anytime you want to draw the direction of an electric field strength, use your thumb. Use your thumb. You place the current. Now look at what happened. Let's say I have a wire like this. I have a wire like this, and then we now place a current. This current is now going downwards. How do you think the direction will be? I have to place my thumb down, and then you curve like this. You see that this thing is going to go anti-clockwise. Okay, it's going to go clockwise. This one is anti-clockwise. This one is going to go clockwise. Right? It's going to go like this, clockwise. Because my thumb is like this and my thumb is now downward and my hand is now like this. It's going to go do it. This according to this camera, you know that I'm opposite the camera, so it will be like opposite. So do it yourself. Okay. So that is how to draw the direction of an electric field strength. So that is that. Now the next thing is that the strength of the force depends on the angle between the wire and the field. Okay, that's another thing he determined. He discovered that that the strength again depends on the strength on the force depends on the angle between the wire and the field. All right, that is that. Now another thing he discovered that look at this now. Now look at this. If I have an electric field like this, there's an electric field like this. Okay, electric field strength like this, electric field like this, and I have a wire like this. This is a wire. Now, this guy discovered that the angle between this electric field and the wire determine the strength of that electric field. Now, if you look at this one now, this electric field, this wire, and the electric field is perpendicular to each other. Now that is where you get the maximum strength. Okay, the maximum strength is what? Is when the wire is perpendicular to the electric field. Please, this is an exam question, note it down. The maximum electric field strength, is when the wire is perpendicular to the electric field. Then the least of it is when it is parallel. Okay, the more you are moving like this, the more the strength is reducing. Once the wire is now perpendicular, maybe the wire is now like this, is now parallel. When the wire is now parallel to this electric field, then the strength is zero. It will not have any strength, or that's the least strength to be zero. In fact, the strength will even disappear. It will disappear. Okay. Now he said that the force diminishes at an angle zero. Yes, that is when it is parallel. When it is parallel, it does not make any angle. The angle is zero. And if the angle is zero, it means it has no strength. Alright? Now the next one we look at is Maxwell corkscrew rule. Maxwell corkscrew rule. You have to know all these things because they are all exam questions. Maxwell corkscrew rule. Okay, they say that this states that if we imagine ourselves driving a corkscrew in the direction of the current, then the direction of rotation of the corkscrew is in the direction of the line of force. Okay, you have to just know that one. Okay, the next one we'll talk about is the thumb. Okay, we have talked about that. The right hand thumb rule. I've told you that in the right hand thumb rule, you place your thumb to in the direction of the current, then the direction of the field is now the remaining forehand, the way it is curving. Okay, I've already said that before. Okay. Okay, look at an example. Let's give an example. Example one, for the right hand thumb rule. Example one, let us use right hand thumb rule to get this. Example one said a wire carrying, okay, wire carries an electric current from west to east. Then I say the direction of the magnetic field. Okay, find the direction of the magnetic field at a point directly below the wire. Okay, now look at this question. This is a very simple question. Solution. Now let's find it. They say that a wire carrying a current, electric current from west to east. Look at it. I have my cardinal point. This is my cardinal point. Okay, this is my cardinal point. The north, south, east, west. Okay, let me draw it from west to east. This is my west to my east. So this is the direction of this current. Now, if this is the direction of the current, that means I am going to place my thumb like this. If this is the direction of current, I'm going to place my thumb like this and then curve this like this. Curve this like this. So this is going to go, I don't know how to draw this circle. Like the circle is going to be rounded like this. It's going to move from north to west. You are seeing it like this. Okay, so that is how the movement is. But they are trying to ask us the direction of the magnetic field at a particular point, and that particular point now they say is below. If it is below, then I'm going to draw a tangent below. Let me draw a tangent below like this. This is a tangent below. Okay, because this is going. Don't know how to place it. No, this is not. Oh, my problem is drawing. If you have the circle like this and they say below, okay, you're going to draw a tangent to the circle. The circle is going to be in this form. Are you with me? If the circle is in this form, then your tangent is going to be pointing to the north. Don't know. Oh God. I don't know how to show you. Don't know how to show you the thing because my drawing is awkward. But the direction is going to be to the north. Just imagine it yourself. This thing is standing like this. If it's standing like this, then the tangent is going to be like this. So it's going to be pointing northward. Okay? This is going to be pointing northward. You know that this thing is going like this. Like it's going like this. So you are going to follow that same direction to draw your tangent. So it is going to be north, to be pointing north. So from the bottom of it, you go the same way you are going. From the bottom, you are going the same way. So, but if it's on top, you're on top going like this. So it's going to be south, but it's from the bottom, it's going to be north. The same direction as you are holding this thing. You know that this thing is like this, and I'm holding from south to the north. You see the way I'm moving. So since they say from the bottom, the direction is going to be like this. I see it is going to be north. It's going to be pointing north. So that is what I mean. But I don't know how to draw a circle so that you understand what I'm saying. You can try it by yourself. So number two said, suppose you are standing in your room and you find an electron moving from the ceiling moving from the ceiling to the floor. Okay, right in front of you. Right in front of you. Then they now say find the direction of magnetic field towards you. Okay, towards your right. Okay. Now, if you look at this now, you will see that maybe I'm standing like this. Okay, and I now saw an electron moving from up to down like this. Okay, and you know that the movement of a charge, okay, the movement of a charge, if it is a positive charge, the movement of the current is going to move in the same direction. But if it's a negative charge, it's going to move in opposite direction. So if the electron is moving from up to down, that means the direction of the current is moving from down to up. So this is the direction of the current. This is the direction of the current. If this is the direction of the current like this, then I say from my right, I'm going to hold this thing like this. I'm going to place my thumb to be in the same direction with the current. Okay, then turn like this. Then now say from my right, if I'm moving from my right to the left, this is a circle. This is the circle like this. Then I am going to draw the same from my right. Okay. Remove your hand from here. I'll beat you. So I'm going to have that. Okay, from my right like this. I'm going like this. So it is going to be northward, right? So it's going to be northward. All right. Because I am going from my right. Look at the way from my right. If this is the current is moving from down to up, then I'm like this. They say at the point right. So from my right is the east. So it's going to be moved. If I draw a tangent, the tangent is going to be pointing west. So the answer is west, not north. Okay, from the east, you are moving to the west. So the direction is pointing towards west. That is how the tangent is going to be. I don't know how to draw this thing, but try to do it, then I know you understand it. So it's going to be to the west, right? Okay. Is it? This is going to be, is it like this? Okay, sorry. The tangent, if this is a circle, okay, let me look for a circular something. It will help me get it right. Let me look for something. Okay, let me use this as a circular something. Now, if this is the circle, it's moving like this. If I draw a tangent to this circle on my right, I'm going to draw a tangent like this. So it's going to be north. So the answer is north. It's not. But in the other one I said, let us repeat the other one. The other one said that it is moving like this. So if it is like this, now, and they say I should draw it on the bottom. The bottom my tangent is going to be like this at the bottom. You see it? My tangent is going to be like this at the bottom. So it's going to move east. It's going to move what? East. Is it? Yes, it's going to move east. So for the other one is east. Why this one is north? Please make correction. Now the magnetic force on a charge is given by, you know that force is a vector quantity, is given by, the force is equal to what? Q in bracket of what? V cross B. V cross B. This formula is very, very important to note. You know that charge is a scalar quantity. So the V is the velocity. Velocity is a vector quantity, and then your B is what? The strength of what? The magnetic field. and it is what? A vector quantity. So this is the formula in calculating the magnetic field strength. The magnetic field. So if you want to get the force now, if you want to get the force, this is the force. Then if you want to calculate the magnetic field strength, you have to make this subject of the formula. All right. But you should know, according to vector analysis, that the magnitude. Okay, let's take the magnitude of both sides. We'll take the magnitude of both sides. That is the magnitude of this is equal to what? The magnitude of a scalar quantity is the same thing. So okay. So the magnitude of a scalar quantity is empty. So this is going to stay here, and I have the magnitude of what? V cross magnitude of B. All right. But according to cross product, we know that what? That magnitude of V cross B is the same thing as what? Is the same thing as what? Magnitude of V times magnitude of B sine theta. Okay? If you remember this in your vector analysis, you can go and watch my video on vector analysis to help you to understand this. So if we now substitute this thing here, I'm going to have that F is now equal to what? Q V B sine theta. Okay? Because the magnitude of this will give you a scalar. That's why I just wrote it like this. The magnitude of this one will give you equally a scalar. That's why I wrote it like this. The magnitude of this will give you a scalar. So this is scalar calculation. If you want to calculate it, this is a scalar form. This is the scalar form. The scalar form. Okay? Why this one is called the vector form. Okay? The scalar form and then the vector form. Now, let us do something. There's something I want us to do. Now, let us write where my F is equal to what? Force measured in what? In Newton. The next thing is what? My Q is what? Charge. Charge measured in what? In coulomb. My V is what? Velocity. Velocity measured in what? In meter per second. Then my B is what? The electric field strength. This is what? The magnetic field strength. Magnetic field strength. The magnetic field strength measured in Tesla. Tesla, like this. T, measured in Tesla, T. Now, okay. With this, let us calculate. Let us do something. Look at this thing now. I have that my V, okay, is equal to what? Q in bracket of V like this cross B. Now, do you know that velocity is displacement over time? I hope you know that. Velocity is what? Displacement over time. Displacement over time. Displacement over time. If you know that this, let me say that let displacement be, let me use L to represent displacement, okay? Then L over T. Now let us substitute this thing here. I'm going to have that my F like this is equal to what? Q in bracket of what? L over T cross B, right? But you know that time is a scalar quantity, displacement is a vector quantity. So let me put cap here to show that this one is a vector quantity. Since this one is a scalar, it can come outside. If it's coming outside, I'm going to have that my F like this is going to be what? Q over T in bracket of L, a vector, cross what? Your B, that is a vector. Now, do you remember Q over T is what? Charge per unit time is what? Current. Q is equal to IT now. You know your formula in electricity. Q is equal to what? IT. So my I is going to be what? Q over T. So now, if my I is Q over T, I'm going to have that my F like this is equal to what? Your I in bracket of what? L cross what? Cross B. Okay? Now, this is the vector form when you are talking about the length and the current. Okay? This is talking about the charge and the velocity. So this is the vector form. The vector form of it. Okay? If we do the same thing, if we repeat the same thing we have here, we know that L cross B magnitude, if we are taking the magnitude of both sides, okay, let's take the magnitude of both sides, that is magnitude of F like this, all right, is equal to, this is a scalar quantity, so it's going to be here, okay, in bracket of magnitude of L cross magnitude of B. like this. Magnitude of S cross B like this. Okay. But according to vector, we know that what L cross B with magnitude in it is something as saying magnitude of L, magnitude of B, then what sine theta. So which shows that you know that magnitude of this. So you know that magnitude of f is going to give you a scalar quantity. So we say just f is equal to what? I is already a scalar in bracket. Then this one will give you what? L a scalar, B a scalar, sine theta. So this is what? This is the scalar form. The scalar form. Okay? Where your what? Please write it down. Where your F is the force in Newton, your I is current in Ampere. Your I is current in Ampere. L is what? Displacement or distance in meters. Then your B is what? Your electric field strength in what? In Tesla. Then what? Or Tesla. Don't know. Is it Tesla or something? Just T. Tesla or Tesla. I don't know. I don't know the pronunciation. So I call it Tesla in T. Alright, where your theta is now the angle between them. Okay? Or angle of inclination. I hope I can clean here. Now, there is another thing I need to show you. Let us keep getting some equation. Okay? Let me write all the equations I've already gotten. The first equation I got is that what? That F like this is equal to what? QVB, right? QV cross B. This is for vector, right? That's equation 1. For scalar, we say that what? F is equal to what? QVB sine theta. Equation 2. Then we now got again that F is equal to what? I in bracket of what? Displacement cross B. Okay? Which this is for the vector, equation 3. Then we now got that what? That ILB sine theta. This is for the scalar form. Okay? Now, there's another thing I need us to do. Let us talk about some little things. Now, let's talk about velocity. When we want to get the velocity selected moving charge. Now I want to calculate the velocity of a particular point, okay, of a particular moving charge. What do? We know that, note, right, like that velocity selector moving charge. Okay, velocity selector moving charge. We know that our V is equal to what? QVB. We know this thing. We know that force is equal to QVB. All right. Then we equally know that force in an electric charge. The force in an electric charge is given by what? Can you remind me? Force in an electric charge is given by. I know that electric field strength is equal to what? Force over charge. So therefore, my force will now be what? Charge E. Okay, that is QE. All right. Now, if I equate these two things now, if I equate them, I'm going to have that what? Q. This is for electricity, and this is for magnetism. So QVB is equal to what? Is equal to QE like this. So if Q take care of Q, I'm going to have that my V is equal to what? E over B. This is a very important equation, a very important formula number 5. You need to know this, please. Now, if we decide to calculate the radius, let us get the radius, because you know that this magnetic field strength is traveling in a circular path. Let us get the radius at any point. Let us get the radius. For the radius, okay, if you want to get the radius, you will know that F is equal to what? QVB. This is a very important formula to note. Okay. Now we know that centripetal force is equal to what? mv squared over r. Don't forget this. Go and watch my video on the circular motion. If I equate these two, I'm going to have that QVB is equal to what? mv squared over r. So if I make r solid of the formula, I'm going to have that my r is equal to what? Mv over what? Qb. This is another very important formula, equation 6. All right, this is a very, very important formula. So the last thing we're going to talk about in formula is what we call the Lorentz force. The Lorentz force. The Lorentz force is the total force, okay, the total force exerted by an electromagnetic field. It is electricity and the magnetism. When a material passes through an electromagnetic force, it experiences a electromagnetic field, okay, the force that is exerted in two of them, the total force. So Lorentz force is given by F is equal to what? That is the total force. Lorentz force is the total force. The total force is equal to what? The force in electricity plus the force in what? In magnetism. Okay? And we know that the force in electricity, I told you before, that charge, that electric field strength is equal to what? F over what? Newton per coulomb, or F over charge. So therefore my F is going to be what? QE. So let us put it down. This is QE, all right? Plus, remember this one does not change. QVB. So now, if you now bring out this, you're going to have, if you now bring out what is common, you're going to have that my Q is equal to, Q in bracket of what? E plus Q outside. Q is already outside here, so I am left with what? V cross B. Please, this vector, and then the force is equally a vector. Okay, this is equation 7. These 7 equations are very, very important to note. Then you are done in the calculation concerning this. Then we'll still go further to other things. So, but for this level, let us now solve some calculations. All right.